This lecture, we're going to talk about one of the last applications of integrations that we're going to talk about in this class. There is another chapter, chapter 9, where we talk about differential equations, which, yeah, we use integration in that as well. However, this will be the last formal application of integration, and possibly one of the more interesting one, I would say. If you have any interest in statistics or you've taken Math 10 or SAT class at the end, you probably have some understandings of basics of statistics and probability. But I don't think you've probably seen the approach we take in this section for probability part of it. So this is using the intuition, using the understanding of the probability, and turning it into, using integration, turning it into something that opens up the door to a lot of formulas that you guys get to use, or that, of course, the proof of them are available if you guys want to verify some of the formulas you use in your stat class and why those work. Then you can look at the proof of them, and a lot of those proofs involve integration. And the basic simple concept of, say, normal distribution is really the z-table that you have in the back of your stat books. All of those are basic calculations of integrals and numeric approximations of integrals. So what's the idea here? The idea here is we start by defining what we call a probability density function. So a probability density function, this is, by the way, 8.5. Our density function f of x has two properties that we want. One of them is that it has to be always greater than or equal to 0. You don't expect a negative probability for anything. 0 is okay, you can have 0 probability of an event, but you don't expect it to be negative. And second property is that the integral from negative infinity to infinity f of x dx would have to be 1. So basically what I'm talking about is, if I have this could be a probability density function. It's always positive as long as the area under the curve from negative to infinity is 1. If that's the case, then it's a probability density function. Now, it may not mean anything. It may not correspond to any specific probability that you're trying to use, but it doesn't take away from it being a probability density function, PDF. Okay. I expect you guys to know at this level and the level of calculating some basic probabilities. Again, this is not a stat course. We don't get too in depth in this topic, but I do expect you guys to be able to verify something as a probability density function and calculate some basic probabilities for that function. So for an example, let's do a quick example, and this might be actually a homework problem that I have assigned, but no problem. Let's just go ahead and do it. This is from 8.5, number 5. There's very few problems that I can actually expect you guys to know from this section, just because we don't go too far in depth in this. But the ones that, again, I do should basically explain the concept to you guys. And if you understand those, then you should be fine for the purpose of the assessment and test for this class. So number 5 gives you the f of x that says f of x is equal to, and again, this f is supposed to be, the questions are about this f being a PDF. So it gives you an f that says c over 1 plus x squared. And then it says for what values of c is this f a probability density function. So two things you want for something to be a probability density function, it has to be positive. So as long as my c is positive or 0, then this will be satisfied. It cannot be 0 because then f of x would be constant 0 function. There's no way the area under the curve would be 1. So I'm hoping for a positive value for c. And then I find c by setting the second equation. So I say negative infinity to infinity of c over 1 plus x squared dx. I want this to be 1. So that's what we want to do. So the way you handle this is you're going to integrate from negative to infinity of this. And the way we did that was by writing it as integral from negative b to 0 of c over 1 plus x squared dx plus as limit as b goes to infinity. You could alternatively, I don't know if you guys remember, you could do b to 0 and let b to go to negative. Again, whatever your flavor is for this, but and then limit as t goes to infinity, 0 to t, c over 1 plus x squared dx, and set that equal to 1. For something like this, because I know it converges, that's from section before, I could actually do negative b to b. That's not a problem because I know it converges. But if I didn't know it converges, I would have to do this. And if either of these diverges, then you could just say, well, it doesn't exist. But as I said, again, because I know it converges from chapter 7, then I could just skip this step and go directly to negative b to b, limit as b goes to infinity of c over 1 plus x squared dx. Again, this seems like a subtle thing, but mathematically that's a very important thing because we are not sure. If we are not sure that this converges, then you have to do it in 2 parts. And if either of these diverges by the concept of the improper integrals, then that part just disappears. I'm sorry, then that whole integral would be canceled out. That cannot be, that would not converge and it's not going to be equal to 1. Wrong choice of words. But anyways, so this one, again, this is an even function. So I can rewrite it as 2 limit as b goes to infinity of 0 to b c over 1 plus x squared. 2 limit as b goes to infinity of c tan inverse of x from 0 to b. Just 2c limit as b goes to infinity of tan inverse of b minus tan inverse of 0, which is 0. 2c limit as b goes to infinity of tan inverse of b. As b goes to infinity, remember our arctan looks like this. As b goes to infinity, arctan goes to pi over 2. So 2c pi over 2, which is pi c, not pi c's, I guess, pi c. And set that equal to 1. So pi c is equal to 1 or c is equal to 1 over pi. So your function is 1 over pi replacing c with 1 over pi. Guarantees the area is 1. And since it's positive, no problem. So it is exactly what I want it to be in order for it to be a proper density function. Part B says for what value of c, for that value of c, find probability of x being between -1 and 1. Now, probability of random variable x being between -1 and 1 is basically saying I want that to calculate the area below the curve from -1 to 1. So that's -1 to 1 of the equation of the function, which is 1 over pi 1 plus x squared dx. So whenever they give you probability and they give you constant, those are supposed to create your bounds. Now, again, now it's basically just integration. You're going to say, okay, well, this is going to be limit. No, sorry. It's going to be, because it's an even function, it's going to be twice of the integral from 0 to 1 of 1 over pi 1 plus x squared dx. Pi comes out as well, 2 pi. And the derivative 1 over 1 plus x squared is tan inverse of x from 0 to 1, which is 2 over pi tan inverse of 1, which is pi over 4, tan inverse of 0, which is 0. So I get 1/2. So that's how you calculate that. Okay. So basically what I want you guys to be able to do is if problems gives you a function that says verify that this is the probability density function, you can do that. If I say find the C for which it would be a probability density function, you can do that. Then probability between two values, you should be able to do that as well. One of the nice PDFs that you can very easily verify some properties is a uniform density. Uniform density, basically, it's, say, if this is A, this is B, you have the same probability for everything in between. And in order for the area under the curve to be 1, you want the height to be 1 over B minus A. So B minus A times 1 over B minus A, the area would be 1. So basically, it's 0, 1 over B minus A when X is between A and B, and 0 otherwise. That's the definition of it. And then if somebody says, what is probability of X less than or equal to A, even or less than A, and we usually we find a random variable function, we write it with capital X. Or less than A, they're the same. So less than or equal to less than, it doesn't make a difference. It's going to be 0. Because there's no probability before A, right? Now, if there is some number C and some number D in between A and B in that order, and someone says what's probability of X being between C and D, again, the equal or not equal doesn't make a difference. It's really that area. I'm integral from C to D of 1 over B minus A dx. Or D minus C times 1 over B minus A. That's how you calculate those. Uniform density is really easy to see, visualize what's going on. Okay. And that's basically it. That's basically it. If you can calculate the area under the curve, you basically can calculate the probabilities. Now, one of the features of a probability density function would be something we call the mean or expected value. That's really your average. You know how you calculate grade average? You add up all the points divided by the number of points or number of grades. That's what it is. Average, right? Average expected value. So for example, if somebody says, let's go to the rolling a die, right? If you have a die and you just roll it, there's 6 different values you can have, right? You can either have 1, you can either or have 2, or have 3, or have 4, or have 5, or have 6. So if you roll a die, any of these 6 can show up. If someone says what is the expected value or what's the average of those, you probably say, you should say is adding them all together and divided by the number of. So this is the expected value. Or sometimes we write it with Greek letter mu for expected value or mean. Now the thing with that is, though, in this case you get 3.5. And that's okay, because that is what the average is. But the problem is none of those 6 numbers is 3.5. So you cannot always expect your average to be one of the numbers you have. In this case, it's a discrete case. So you don't have a continuous function. But nonetheless. Now, if I think about this slightly differently about this, I can say it's 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 plus 4 times 1/6 plus 5 times 1/6 plus 6 times 1/6. That's really what happens if I divide each of those by 6. And notice 1/6 is a probability of each of the events. The chance of getting a 1 in a first row, in each row, is 1/6. The chance of getting 2 is a 1/6, 3 getting a 1/6. Sometimes it takes sometimes hard to accept that when you roll a die, the probability is 1/6, because you're like, well, I could roll it. In some games that we play, right? I could roll it, and 5 times in a row I get a 1, and I don't even get a 6. So in your mind, you're like, well, then the probability of getting a 1 is higher than getting a 6. Assuming a fair die, that it has the equal probability for each side, that doesn't take away from the fact that probability of each event is still 1/6, because we're talking about long term. The idea here is if you do this thousands of times, and again, I'm exaggerating, but thousands of times, then each of the faces are going to show up a 1/6 of that many times. So if you do 6,000 times, you have, say, 1,000 times 1, 2, 3, 4, 5, or 6. Again, this is not a very rigorous way of talking about this, but I'm just saying, like, that's the idea. That's the idea. But you could roll it 100 times, and each time will be a 1. It probably not likely, obviously, but doesn't take away from the 1/6 probability. Anyways, going back to this problem, to calculate the average, I can just calculate it by multiplying each number by the probability of that number. 1 times 1/6, 2 times 1/6, 3 times 1/6. So basically, we can take that to the continuous case, and I say, if I want to calculate the expected value of x, I can do it by integrating from negative to infinity of x, f of x dx. X is the number, f of x is the probability of that number. So if somebody says, what is in the last example, which wasn't a part of the problem, but if somebody says, okay, consider, again, f of x equal to 1 over pi 1 plus x squared, and says, what is your average? I say, well, that's negative infinity to infinity of x times 1 over pi 1 plus x squared dx. So it's going to be 1 over pi into from negative infinity to infinity of x over 1 plus x squared dx. Again, I understand, I know the convergence. So it's going to be 1 over pi, limit as b goes to infinity of negative b to b, x over 1 plus x squared dx. And I notice that x over 1 over plus x squared is an odd function. So this integral over symmetric interval is 0. So 1 pi. So expect the value for a 1 over pi 1 plus x squared is 0. Not unlikely. Nothing wrong with the calculation, nothing wrong with the result. Can happen. Now, one of the other other examples of continuous ones is normal distribution. Normal distribution, your classic bell curve, is a continuous density function. Looks something like a bell curve. The equation of it is 1 over sigma, and I explain what that is, square root of 2 pi e to the negative x minus mu squared over 2 sigma squared. Now the parent function for this is e to the negative x squared. You just have some numbers or constants to, sorry, you have some constants and numbers to be in there. So like this part is supposed to make sure that the area under the curve is 1 when you integrate it. So that's why you have this piece. And mu and sigma, of course, have the role of mu is your expected value or your mean, as it was before. Sigma is what we call standard deviation. We don't get too much into standard deviation in this class. And again, if you have taken a stats class, you probably have talked about it a lot. But basically, those constants affect each normal distribution and make it spread out more or less and shift the mean value to the left and right. When you look at the graph of normal distribution, where your inflection points are, those are one standard deviation. If this is mu, that's mu minus sigma. This is mu plus sigma. They're one standard deviations away. And then you can just take steps to go to the next and next. Again, we don't do much with it, but if you want to calculate it, you can show that 1 over the negative to infinity 1 over sigma root 2 pi e to the negative. That's, I'm just rewriting that in a better handwriting, and while you can actually see it this time. This is actually going to be 1. If you have interest, you can calculate it. Would not be too easy at this level. You may need some machinery to help you, but you should be able to understand the solution. Now, and of course, if I want to calculate anything in between, if I want to calculate probability of x being between a and b, then I would have to integrate this from a to b of this integral. And that will give you a probability that you're looking for. Now the problem is such a process cannot be done because this does not have an antiderivative. The parent function e to negative x squared doesn't have an antiderivative. So you really cannot do this exactly. And that's why when you look in the back of the stat books, a lot of them have what we call z-table or the table of normal distribution. And all those numbers calculated there, they are done most likely using Simpson's rule. So you get those values there. So those tables are actually created by numeric approximations of this integral. They're doing from negative infinity to x usually, so that's what it is. And the sigma and mu in that table, actually mu is 0 and sigma is 1. So the table of the z table in the back of your stat books is a standard normal distribution, which your mu is 0. So basically what you will have for those is sigma is equal to 1, so you get this, and mu is equal to 0. So that's basically what you will have. This is still going to be 1, but when you do different probabilities, then you have to calculate this. And to calculate this integral, they use Simpson's rule. And that's how you get the numbers in the back of the book. Not your book, but stat books. And that's why you see some different tables from different books. They have different level of accuracy in the table. That's just because they're using different partition size for their Simpson's rule. And now they can just do those with technology anyways. A lot of calculators or websites help you. There are apps that will help you calculate normal distribution. Your TI calculates it too for you. And that's basically 8.5. 8.5 is not a fancy section. It's just basically one last application of integration for you. And the level that I want you guys to know is as a level of those problems that I assigned as homework and I did in class right now. Nothing much far beyond that is needed. Okay, I hope this was helpful. Basically, the other problem, I don't want to do a lot of problems because basically all of them are the same thing, but more practice. So just do those and then ask me if you want me to go over any of those for you. Other than that, I hope this was helpful. Thank you.